All right, so Snell's Law Part 2. This is going to be using Snell's Law to sort out light-related refraction, okay? So let's just get this nailed down here. Snell's Law Part 2. So who can just remind me before we get going here, what our little relationship was that we had laid down? I think it was this, right? N1 sine theta 1 equals N2 sine theta 2. Now, this is actually part of that bigger equation that we learned yesterday, right? Which went V1 over V2 will be the same ratio as sine theta 1 over sine theta 2. And it will also correspond to wavelengths 1 over wavelengths 2. And then the tricky part, N2 over N1. This ratio is inverted from the other ratios, okay? We'll talk about the reason why that is in just a minute. So if I take just a specific part out of this, because this is what's going to be important for light rays or light waves, if I take this and this out, I just want to show you what you're going to see. What you'll see is you'll see this relationship. Sine theta 1, sine theta 2 is equal to N2 over N1. Now if we rearrange this formula, you should be able to algebraically convert it into this. So that is challenge number 1. I'm going to pause, and you can pause if you're watching this for the first time, and I want you to exchange this for this, step by step, algebraically. All right, so hopefully you've had a chance to rearrange, I guess, if you want this formula into this one. But basically, the rationale is if you start on the right side, multiply by N1, that brings it over to here. And you have N1 sine theta 1 over sine theta 2, multiplied by sine theta 2 on this side, and that brings it over. They sometimes call that cross-multiplying. Okay, so let's try a problem with this. Now, just remember from last time that that N value is called the refractive index, okay? Refractive index. How do I calculate a value for a refractive index? Do you remember? Correct, C over V. Almost made a mistake with that yesterday, but we corrected it in time. And what does that mean about the value of N if V is lower? So let's say we have something with a really high refractive index, like a diamond. So let's just, can I draw a diamond here? Let's fire a diamond in here. Okay, and it turns out that diamond has a refractive index somewhere around 2. And I'll just get the exact number here. Yeah, so it actually turns out that diamond has a refractive index even higher than 2. It's 2.4. Okay, so N equals 2.4. Well, what does that mean about the velocity of light inside a diamond? Does that mean it's low or high? Versus, let's say, like, I don't know, like some plastic that has an N value equal to 1.2. Does light travel faster in Exhibit A, or does it travel faster in Exhibit B? Where does it travel faster, A or B? A. It travels faster in A. In other words, because essentially you have this relationship, right? N is inversely proportional to the velocity of light inside that substance, okay? So as velocity decreases, N gets larger, right? In the case where you get something over 2, that must mean that you essentially have a ratio of 2.4 between these two values, okay? Are you with me? No? Not good with fractions? So well, it's just like this. Like, let's just do a side example if that's not working for you. Let's say you have 10 on the top and you have 2 on the bottom, or you have 5 on the bottom. What does this equate to? What's the ratio between 10 and 2? And what about 10 and 5? 2, right? So if we're saying that these are sort of similar to n values, the lower this number gets, the higher this number gets. Do you see? The lower this gets, the higher this gets. The more times it will go into C, right? Hopefully that makes sense. Well, the lower the velocity of light in the new substance gets, the lower it is, the higher the n value gets, right? So in the case of here, like what if we drop this down to 1 on the bottom? Well, then you'd get a value of 10. What if you dropped it down to a half? Then you'd get 20, right? The smaller the number in the denominator gets, the larger the answer becomes, okay, or the equivalency becomes. Okay, so let's, just to reinforce this concept, do this for me. Find the speed of light when light is inside a diamond. Inside a diamond. And one thing to remember, C is always going to be equal to 3.0 times 10 to the 8 meters per second. Digressing. So, okay, let's look at this. So if we know that N equals C over V, let's say what we want to know is we want to know the velocity inside diamond in this case. If N is about 2.4, right, and C is 3.0 times 10 to the 8 meters per second, don't worry, I'm going to rearrange it before I do anything. Okay, this is essentially what we're solving for. Now, we like to rearrange formulas before we do anything, so let's see how we go about doing that in case you don't know. First thing probably is get numbers off the bottom, so multiply both sides by V, so NV equals C. That's actually another way to write the refractive index rule, that the refractive index times V will always equal C. And then you get this, right? V equals C divided by N. So 3.0 times 10 to the 8 meters per second divided by 2.4. Yeah. So just to write this down, 1.25 times 10 to the 8. And that's meters per second. And if you're following sig figs, you should technically only have 2, so it's about 1.3 times 10 to the 8 meters per second once we round it correctly. All right, so moving on from this question, we now know that light will slow down when it enters diamond. We solved the problem, if we know 2 velocities yesterday, we solved the problem like this. If you go back up, and you know 2 velocities already, where are we? Way back up here. We actually should be able to solve this problem with just this information. But Snell's law is quite often written like this, and you're just given the index of refraction, and that's an extra step, right? If you had to find the velocity first and then use this formula, it would be an extra step to solve it. And you can solve it directly on the ratio of n2 to n1, right? Now, if you remember, someone said, why is the ratio of n2 to n1 inverted from everything else? The reason why is because n2 gets larger when velocity gets smaller. So its growth is inverted to the rest of these. So in other words, if velocity 1 is faster and velocity 2 is slower, then wavelength 1, right, will be higher and wavelength 2 will be lower, or this will be longer and this will be shorter. But the opposite is true, right? For the place where light is traveling faster, then that is where the n is larger. Where the n is smaller. For the place where light is traveling slower, that's where the n is larger. Hence, the orientation of these has to be inverted, okay? So the ratio of n2 to n1 is still relevant, but it's the inverted ratio because of the way that you come around to solving for refractive indexes, and that is that, you know, as velocity gets slower, they get higher. So, what is the refractive index of air? And it turns out that it is essentially, for all intents and purposes, the same as in a vacuum. So we say n in air is just equal to 1. That's not quite exactly true. Light does travel a tiny bit slower in air than it does in vacuum. But for our purposes, it's such an insignificant or small difference that we just assume that in air, n is equal to 1. Are you cool with that? Okay, sweet. And then in diamond, we said that n was equal to 2.4. So we'll call that n2. n1 and n2. Okay? This is faster, and this is slower. Again, for reasons explained before. As this number increases, that means the velocity is decreasing. Where would the light have a shorter wavelength? In here or in here? Okay, so we keep the frequency the same, so that must mean then that the light will have a shorter wavelength inside the diamond. Okay? An interesting question is, what would that do to the color of the light in the diamond? Does it change? Is the color of the light based simply on the frequency, or is it based on the wavelength? Well, it's pretty hard to get inside a diamond and look. So I don't know if we can really answer that question. Maybe somebody can, but I can't. So I don't know what happens. Okay? So let's write in our angles here and see if we can solve something. So let's say, well, we have theta 1 here, right, as measured from the normal. We have theta 2 there, again, as measured from the normal. And the normal, of course, is just a helper line that we draw in perpendicular, right? And just to reiterate, these wave rays, they are showing the input waves and the output waves. Whether light is actually a wave like we imagine is sort of, it's not really a wave like we would think a water wave is. It's actually something more complicated. But we don't need to really get into that. But, you know, Snell's law also works with water as well as light, so we could have the same kind of concept. And then they change directions once they get into the new medium. So if theta 1 equals, let's say that is, I don't know, 50 degrees. Solve for theta 2, okay? So in order to solve this problem, you got to use Snell's law, and you say n1 sine theta 1 is equal to n2 sine theta 2. And we want to solve for theta 2, so let's do some rearranging. The first thing is, let's divide n2 off of this side and put sine theta 2 over on the left side. So sine theta 2 can come over here. We divided n2 off of this side, so n1 sine theta 1 divided by n2. And now, in order to remove the sine theta part, we have to inverse sine the other side. Okay, so just finishing this up. Okay, so then, in order to get this where we want it, we have to inverse sine this. I just want to solve this, and then we can be done. So n1 was air, all right, so that equals 1 times sine of the input angle, which we made 50 degrees, all over 2.4, the refractive index of the secondary medium. It's not always going to be air. Like, it could be water to diamond. Well, water has a refractive index of, like, I don't know what is it off the top of my head, like 1.4, say. In that case, that would be a 1.4. But in the case where this is just 1, multiplying by 1 makes it essentially irrelevant. So let's get our calculators and finish up. So when you solve this, you should get somewhere around 18 degrees, about 18.5 degrees. So 18.6 degrees, okay? So in other words, we bend towards the medium as we slow down, just like we would expect.